Okay, so let's wrap this up and prove the chain rule. So fortunately, the statement of the chain rule is pretty much identical to what you've probably seen in the past, but the proof is just a little bit more difficult than one might expect. So let me write down the statement. Okay, so this is 28.4. So the chain rule says if f is differentiable at a and g is differentiable at f of a, then g compose f is differentiable at a and g compose f prime of a equals, well, let me put it on the same line here, equals g prime of f of a times f prime of a. Okay? So, right. So the question is, so this hopefully looks basically the same as what you've seen in the past. The question is, okay, why is this hard to prove? Or, well, I don't know, quote unquote hard. So naively, we might hope to write. Okay, so one might try to write, so g compose f of x minus g compose f of a over x minus a equals g of f of x minus g of f of a over f of x minus f of a times f of x minus f of a over x minus a. Okay. However, this only makes sense for values of x such that f of x is not equal to f of a. Okay. And so the problem is like, right? I mean, so what, okay, first of all, like, why would this help, right? Let's suppose that this actually makes sense. Then all we have to say is like, okay, as x approaches a, this expression just by definition approaches f prime of a, right? And then since f is continuous at a, as x approaches a, f of x is approaching f of a. And so here you see like f of x is kind of acting like the variable right over here. So in both the numerator and denominator, f of x is approaching f of a. And so by some limit theorems, this would also approach g prime of f of a, right? If you kind of think of f of x as like another variable y, if you make some substitution, then it's like as y approaches f of a, this is approaching g prime of f of a, right? Because you have g of y minus g of f of a, and then y minus f of a on the bottom, right? So, however, the problem is like, so this only makes sense for values of x where f of x is not equal to f of a, and it's possible that f of x might be equal to f of a for like any number of like values of x arbitrarily close to a. So like as an example, like a very simple example of this would just be like g of x equals anything and f of x is just like 1, right? Then f of x equals f of a for all x, right? Whatever a might be. So then like g of f of x minus g of f of a oops, over f of x minus f of a times f of x minus f of a over x minus a is not defined for any values of x. So you can see how that's problematic for us. There can be more complicated examples too, like something like, g of x is, I don't know, x squared or something, and like f of x is like x squared sine of 1 over x for x not equal to 0, and then like 0 for x equal to 0, and a equals 0, right? So then it turns out, f prime of 0 is 0, but f of x equals f of 0 for x arbitrarily close to 0 for values of x arbitrarily close to 0. So this expression becomes undefined, f of x minus f of a. If a is 0, right, then f of x minus f of a becomes undefined at all these points getting really, really close to 0. So the limit of this, the two-sided limit of this, can't exist because there's no open interval around 0 for which this expression is actually defined. So we have to do a special thing, a separate thing for the case where f of x equals f of a for a bunch of values of x getting arbitrarily close to a. So basically, that's how the proof goes. So in the proof, like case 1 is like there exists some open interval around a where x is, or f of x is not equal to f of a. Then we can write the exact same thing that I just wrote before. So we have the limit, and we can basically take the limit of, we can separate the limits into a product basically. So we have g of f of x minus g of f of a over f of x minus f of a, and then times the limit as x approaches a of f of x minus f of a over x minus a. And so this thing approaches g prime of f of a. Boy. Oops. G prime of f of a. And this approaches f prime of a. Showing that this approaches g prime of f of a, it's like not hard, but there is like some kind of a step or two involved here where I guess you essentially have to revert, you have to like go down to the sequence definition and be like, okay, if if xn is a sequence approaching a, then f of xn is a sequence approaching f of a. So then, since the two-sided limit of g of x minus g of a over x minus a exists, then for all sequences approaching f of a, g of that sequence minus g of f of a over the sequence minus f of a should approach g prime of f of a. So yeah, there is like a step or two here, but I'm gonna sort of gloss over that because it's not very difficult. So now case 2 is where f of x equals f of a. So let's say there exists, so there are values of x arbitrarily close to A, which are still distinct from A, but arbitrarily close to A, such that f of x equals f of A. In this case, notice that G compose f of x minus G compose f of A over x minus A is defined, right? I mean, obviously because x is not equal to A, but it equals 0, right? So this equals 0 for all such x. So we just need to show that G compose f prime of A is 0. Okay, because basically, right, this means that there exists a sequence. So this assumption means there exists a sequence Zn in some interval I without the point A, where A is in I, right? So the deleted interval here, where you it's some interval containing some open interval, I guess. Yeah, open interval containing A, but you delete the point A, and then there's a sequence Zn, right, where f of Zn equals f of A for each n. Okay, so this is just a sequence of points getting arbitrarily close to A. Oh yeah, such that Zn converges to A, right? Hold on. Oops. So Zn converges to A, so yeah, such that Zn converges to A and f of Zn equals f of A for all n. So then, for this sequence, G compose f of Zn minus G compose f of A over Zn minus A equals 0 for all n, right? So basically, the value has to be 0. Really, this effectively means that the value of f prime of A actually should be 0. So also notice, right? Also notice that f of Zn minus f of A over Zn minus A equals 0 for all n. So since we assumed the limit as x approaches A of f of x minus f of A over x minus A exists, this actually shows that f prime of A equals 0, right? So we actually can show that f prime of A has to be 0 because we can find a sequence of points, Zn, converging to A, for which this divided difference equals 0, right? So clearly, right, so the limit as n approaches infinity of the divided difference is 0, right? And of course, the presumption that this limit exists, the two-sided limit here, the fact that that exists means that all sequences, right, for all sequences approaching A, the divided difference should approach the limit of this expression, right? So if we found a sequence such that the divided difference approaches 0, that means that the two-sided limit has to equal 0, okay? So we've actually shown that f prime of A is 0, and we just need to show, so just need to show that G compose F. So basically, yeah, we want to show that right. We want to show this thing. We want to show that yeah, G compose F prime of A is 0, right? So to do that, so let's let xn be well, not an element because it's a sequence, be a sequence in, actually, hold on, better yet, let's do, so the book does this in a slightly different order, but I kind of prefer doing it this way. So let's you know, write something, well, hold on. Okay, yeah, so basically what we can basically say is like, okay, if we go back to looking at this expression, this factorization here, right, of this, okay, so what we want to do is for an arbitrary sequence, so let xn be a sequence converging to A, right? And let's say the sequence is in some, you know, interval without the point A. Okay, so let xn be a sequence converging to A. So we want to show that the limit as xn, or the limit, sorry, the limit as n approaches infinity of G compose F of xn minus G compose F of A over xn minus A is 0, okay? So notice that if it so happens that f of xn equals f of A for some n, then immediately we have G compose F of xn minus G compose F of A over xn minus A is just 0, okay? Because this is just G of F of xn minus G of F of A, but F of xn equals F of A. So the numerator is just 0, right? For this, for values where this happens. And if xn is not equal to A, then, or sorry, not xn not equal to A. If f of xn is not equal to f of A, so if f of xn is not equal to f of A, then we have the factorization G compose F of xn minus G compose F of A over xn minus A, right? Or equals, sorry, equals what the factorization we were using before, right? So G of F of xn minus G of F of A over F of xn minus F of A times F of xn minus F of A over xn minus A, right? And so basically the thing we can use is that for the terms, basically, yeah, so the terms are of two types, right? The terms in the general sequence. So remember, xn xn was just some random sequence, right? Xn is basically a random sequence in this interval, an interval for which this limit, the two-sided limit, like an interval for which, you know, the limits, the limit of f of x minus f of a over x minus a makes sense, right, on a certain interval, and then also making sure that that the limit for g makes sense too, right? So on this interval, okay, sorry, basically just an interval where g and f are both like defined, okay? So like an interval where f is defined and f of x minus f of a over x minus a makes sense, and then also where g is defined on the values that f achieves on that interval, right? So xn was like a random sequence in this interval converging to a, okay? And we just wanted to show that this limit is 0. Now we look at this, the terms. We look at the terms in this sequence, right? It's the sequence where we plug in xn. We look at the terms in this sequence, and they fall into two types, okay? One is the type where f of xn equals f of a, where this is just automatically 0, right? And the other is the type where we're allowed to actually factorize it like this. And now the thing is, in this factorization, this factor here should be going to 0, the second factor, right? This should be going to 0. And this stays bounded. Okay. Why does this stay bounded? That's because as xn approaches a, f of xn is approaching f of a, right? And since we assumed that g was differentiable, this whole difference quotient should be approaching some finite number. So this is what they say in the book, okay? So on some interval around a, we must have that, or sorry, on some interval around, yeah, let's say this. We must have that g of f of x, yeah, minus g of f of a over f of x minus f of a is bounded by some constant. Okay, say c. All right, because yeah, because this is because the limit as y approaches f of a of g of y minus g of f of a over y minus f of a is assumed to exist. Okay? So, this means that putting these two things together, right? Clearly, if f of xn equals f of a, then this is just 0, and otherwise we can bound this above by c times the normal derivative for f, right? But then, like in either case, right, this expression g compose f of xn minus g compose f of a over xn minus a, this difference quotient will, in either case, it'll be bounded above by constant times this expression, right? So what I'm saying is that so for large n, we have that g compose f of xn minus g compose f of a over xn minus a is less than or equal to c times f of xn minus f of a over xn minus a. And we know that this term goes to 0. Okay. So Right, and this is true. This is true regardless of whether f of xn equals f of a or not, right? This inequality literally holds for every value of n sufficiently large, because basically once, once n gets large enough, then xn will get into an interval where this expression is bounded by c. Okay, so yeah. I know it's a little bit complicated. Sorry if my explanation was a little bit uh, frazzled or something. But I think they do a pretty good job of laying it out in the book too. So I would recommend, if this was difficult to follow, maybe you give it another shot by just reading what they wrote in the book and see if between the two you can kind of stitch together an understanding of the argument. It's actually not that bad. It really isn't. It's just this one kind of realization that this factor here, whenever it's defined as x gets really close to a, f of x gets really close to f of a, and so this factor has to get closer and closer to g prime of f of a. So in particular, it should stay bounded. Yeah, that's kind of the main realization. So yeah, I think I'm gonna just call it for this video now, and that concludes the lecture. So thanks for watching, and I'll see you in the next one.